Okay, hi everyone. So my name is Katharina, and I'm very happy to present today my first paper named Exploring the Six Worlds of Gröbner Bases Cryptanalysis, Application to Anemoy. So quite the title. Good. Why algebraic cryptanalysis? Why not doing nice statistical stuff? There are a lot of results. So the answer to that is because we are looking at a different sort of primitives. So we are looking at primitives that are specifically designed for CK, MPC, FHE contexts, basically. And those natively work over some very large finite fields. And the performance metric is different to previous designs like SHA or others. So here the multiplicative complexity, verification complexity, is the crucial performance metric. So how can we think about that? We usually have some low degree equivalent round function, and given x and y, does not necessarily mean that we need to really evaluate x, f at x. So consider this very, very short example. So if we have a function x to the power of alpha for some small alpha, and we are given x and y, then we can just simply recompute x to the power of alpha, check if it's equal to y, and if so, then we have verified the statement. This has a low multiplicative complexity if alpha is small. On the other hand, there's also this x to the power of 1 over alpha, and for large fields, this 1 over alpha for small alphas will be super huge. So recomputing this whole thing will be very expensive in terms of multiplicative complexity. But luckily, there is an equivalent formulation. So given x and y, instead of calculating x to the power of 1 over alpha, we can just do y to the alpha and check if it's equal to x. Because we can do this, it's only about verification, not about evaluation. Such primitives are in general called arithmetization-oriented primitives. There were a lot of talks, I think in the spring school there was something, and in the workshops in case you were there. And the main threat for those kind of primitives is algebraic attacks and non-statistical attacks. So this is why we are talking about algebraic cryptanalysis. What do you mean by that? So it's typically either interpolation attacks or polynomial system solving like Gröbner bases, what we just saw, or resultants. So what is this work about? So we're analyzing Anemoy, which is an AO primitive, which was presented at Crypto 2023. There are several results on Anemoy already now, and we had one of the third-party cryptanalysis results in parallel to the free launch, which appeared a bit later on ePrint, to say, not published. And our contribution is a Gröbner Bases cryptanalysis of Anemoy. So you might think, okay, the authors already did Gröbner Bases cryptanalysis, so why like revisit the whole thing? What is our contribution there? So basically, we thoroughly look at the proposed algebraic models, further inspect the degrees, the increasing of the degrees. We investigate tighter bounds for the complexity metrics, and we did really a lot of experiments. Altogether, we framed this whole thing in the 6 worlds of Gröbner Bases cryptanalysis. And what we find, or what we suggest, is that for some instances, the round number should be increased. Good. So I want to start with a very quick recap on Anemoy, because I assume not everyone knows Anemoy, even though it would be nice. So Anemoy is a permutation family, which is based on, or which is built as an SPN structure. So we have these linear layers, which is just round constant addition and matrix multiplication. And then we have a very nice nonlinear layer called the flystyle. And the flystyle has this high degree evaluation called the closed flystyle, where we use this high degree power max, x to the power of 1 over alpha for small alpha. But luckily for the verification, to make this whole thing efficient, it has a low degree verification equivalent. Good. So how is the security now assessed for such AO primitives? So mostly if we have some AO permutation, then we use sponge mode and we get an AO hash function. And then we basically assess the security of this primitive by the security against the SICO problem. So the SICO problem is specifically designed for the sponge mode. It's called constrained input, constrained output model. So for Anemoy, I just quickly show what this means for Anemoy. So for Anemoy, we would fix part of the input and part of the output to 0. And now the goal is to find solutions, basically, to find this y in and y out. So in terms of algebraic attack, this means we want to solve the algebraic model of the SICO problem faster than just brute force. And this is in general done, for example, via Gröbner Bases. Good. What are now these algebraic models for Anemoy? I just want to quickly recap them and not go into too much details. Thank you very much. So the first model which was proposed is called FSICO. And there basically one introduces variables at every round. So you have variables at the round input and at the round output. And then at the input of the nonlinear layer, you have basically only linear functions in the variables, in the input variables, round inputs. And then every round can be described by only 2 polynomials, which are of relatively low degree. So it's basically just degree alpha, because the Qs have degree 2 or 3 either, depending on the field we're working with. Overall, we get 2n equations in 2n variables, but all only of degree alpha. The second model was called PSYCHO. So for PSYCHO, the situation is a bit different. So there we define variables for the very input, so only for the permutation inputs. And then for every round or for every nonlinear Feistel, basically, we introduce only one variable. So this overall leads to only having one variable for every round, but at the cost of increasing degrees. So while for the first model, we have degree alpha for every polynomial, there we have increasing degree for every polynomial there. And depending on the field we're working with, so if it's a prime field, this degree will only increase linearly, even though this might look counterintuitive since we have a power map or a squaring or to the power of 3 of some function, but this is one of the observations. So the degree only increases linearly, and for binary extension fields, it does increase exponentially. Good. So now that we have this model, we can now talk about Gröbner Bases cryptanalysis. So what is basically done for Gröbner Bases and cryptanalysis? So I know the first row or second row knows exactly what this is, but maybe not everyone does. So I will repeat this, but on a more high level view. So we start with some algebraic model, and for simplicity, we just assume we have as many equations as variables. And the first step would be to compute a Gröbner basis with respect to some degree ordering. So typically it's the degree reversed lexicographic ordering. So this is what we saw in the previous talk, which Matthias just constructed by hand. But using some off-the-shelf algorithm like F4 or F5, we can compute the Gröbner basis. Then the second step would be to transform this Gröbner basis into yet another Gröbner basis, but with respect to a different ordering. So with respect to the lexicographic ordering, in this case, using some basis conversion algorithm. And you might notice that the last equation here is univariate, and this is not a coincidence. So for every lex Gröbner basis, this will always be univariate. So we can find a solution, at least for y here, by just factoring this polynomial. So the next step would be to factorize a univariate polynomial. We get a solution for y, eventually back substitute if needed, again get univariate polynomials and solve. And then we end up with solutions. Good, but how does this help now a designer for choosing rounds, or how does this help an attacker? So what do they do? So what they basically do is looking at the complexity of the 3 different steps and then trying to either derive round numbers that should be secured, so meaning that we achieve a certain security level. And the designer typically or very often just fixes one of those steps, which is assumed to be the most complex step. So often it's the first step or the second step. And on the other hand, an attacker would need to show that he or she can attack every single step of a Gröbner basis attack. Good. So for each of those steps, we now need complexities, basically. I spared you with the details of all those formulas, but just give you the high-level idea. So for the first step, this is the degree of regularity that we saw in the previous talk. And then for the second step, it's the degree of the ideal or the degree of the Gaussian space dimension, which is about the number of solutions to the system over the algebraic closure, count with multiplicities, but think about the number of solutions. And the last step depends on the degree of the univariate polynomial. Good. So if we now want to derive round numbers as designers, for example, or say as attackers, is this now secure for these round numbers, or which round numbers would be needed, maybe, we need to somehow formulate for the first step this degree of regularity in terms of the number of rounds. So how to get there? And there are like two possibilities which are used in wild, so to say. So one is to do small scale experiments. So small scale mean small number of rounds, like 2, 3, 4, 5 maybe. Then get the degree of regularity from the experiments and try to find some formula. And this is more of an extrapolative approach and might introduce some heuristic gaps because we can't be sure that this is the true degree of regularity. The second one is using some theoretical bounds, which are unfortunately only upper bounds that we have, and which are typically very loose and are only tied under specific assumptions like having a regular system, which typically does not hold for systems stemming from crypto. Yeah, so we have those two approaches for the first step, and we have the same for the second, and the same for the third. And you might have noticed that I changed univariate degree to the Gaussian space dimension because they're super connected, and very often it's exactly the same, but it's at least upper bounded. Good. So what does this mean now for anemoy? So basically, we used the two systems, F-cycle and P-cycle. We extrapolated the DREG from small-scale experiments. And for the theoretical approach, we use the classical Macaulay bond. Again, it's not tight in this case. And yes, so what do the results look like? So in both cases, for both F-cycle and P-cycle, the Macaulay bond will largely overestimate the degree of regularity we get from the experiments. But even more in the P-cycle case, so the reason for that is that for the P-cycle model, the degrees of the polynomials increases, and the Macaulay bond is computed directly from the degrees of the polynomials, and this is why it continues to more and more overestimate the degree of regularity with increasing round numbers. For the second step, and also the third for the So those are the results here. So the Bezout bound is again computed only from the degrees of the polynomials in our system. And again, in both cases, it overestimates the true degree of the ideal. And what we did then is we used a more dedicated bound or a more precise bound called the multi-homogeneous Bezout bound. And we see that even though it does not change anything for F-cycle, it changes things for P-cycle. So we get a better upper bound, even not great, but better than before, and then with the general Bezout bound. Good. Then how are now these round numbers derived? So I'm explaining this shortly at the example of anemoy, how this was done. So remember, we start with trying to find the number of rounds such that the complexity for a specific algorithm, independence of the round number, reaches a certain level, security level of S, like 128, 256, typically 128. So for anemoy, the decision was made to put this on the first step of the Gröbner Bases attack, so on the degree reverse lexicographic Gröbner Bases computation, and to get the degree of regularity from the experiments. And what was done in addition is to, in this case, use a lower bound on the degree of regularity and not a concrete extrapolation to, on purpose, underestimate the degree of regularity, and so hopefully get some security margin in there. Then the FSECO model was fixed, and an additional margin of 2 rounds was added to account for potential problems with the PSECO model that could arise. Then for the linear algebra constant, this omega we saw, a conservative choice in terms of the designers was made for 2, which is a very usual design choice. And additional security margin was added. So here I just focus on the case L equals 1, so just 2 branches. This is why it's just 2. So in general, it depends on L as well. So, and what we will see in the next slide is that in general, this FSECO plus 2 is not enough to account for the second model. So why? So those are basically our 6 walls that we have. So we have this experimental approach and with the 3 steps, and we have the theoretical approach with the 3 steps. And for the column E1, so experimental approach and GB, here we basically see that the difference between this analysis of FSECO and PSECO is not 2 rounds, but 4 or 8 rounds even. So this 2 rounds was not enough. This is not only the case for the first column, but for others as well. And you might have noticed that there's one interesting point here. So where the FSECO model seems to yield like better results. This is the case because remember that in this world we are using the Macaulay bound. And for the PSECO model, the degrees increase and the Macaulay bound is more and more overestimating the degree of regularity for increasing round numbers. And this is why here, in this specific case, we get better results for FSECO than for PSECO. So in general, it would also help to have like better bounds for the first step of a Gröbner Bases attack in general. Good. And finally, we did a comparison to related work because in the last like 1.5 years, there was a lot of work going on in Gröbner Bases cryptanalysis, dedicated attacks, monomial orderings. So there was this free lunch approach, algebraic free lunch approach presented by Barillon et al. At Crypto 2024. And a resultant approach by Yang et al. Presented at Asia Grip 2024. Basically, what we see in the last 2 columns is that the round numbers that were chosen are not enough to protect against this new style of attacks. So instead of 128-bit security, for example, for 21 rounds for alpha equals 3, the approach by Barillon et al. Suggests that this is only a security of a complexity of about 2 to the power of 118. And the resultant approach said is only 2 to the power of 110, so even less. So how does this now compare to our world, basically? So the argument is, or that we want to promote, is that maybe it is not enough to just fixing one step of a Gröbner Bases attack and then saying, okay, doing all the security analysis just because of one step. Because you might find a different model. You might find an approach where you say, okay, you can maybe even skip the first step really bad. So the idea would basically be to hopefully not only use this first world, but several worlds, like also the second or the third world, and thus get better or more reliable results. So in summary, algebraic attacks are main threat for AO primitives. Many cryptanalysis papers on AO permutation. So I already mentioned those first 3 results, but there are also a lot of follow-up results by Pierre Briot, for example, or Barillon et al. And also by Kamper and Roy, which is going to be presented at Eurocrypt. So what is our contribution again? We framed this whole thing in terms of the 6 walls of Gröbner Bases cryptanalysis to hopefully make this analysis more reliable for designers as well as attackers, or also designers who maybe not have the possibility to find dedicated attacks and construct dedicated Gröbner Bases like off the shelf. We suggest that the round numbers should be increased for some instances, and we got to this result through analysis of both models, employing the multi-homogeneous Bezout bound, and a lot of small-scale experiments, all of which you can find at the GitHub repository of this paper. Thank you very much.
Thank you. We have time for a quick question before lunch.
No one interested in Gröbner Bases or super hungry. I think I went 2 minutes over time.
So I have one quick question. Do you have other applications besides NMOE?
A plan, but not yet done.
Okay. So let's thank Katharina and also Matthias for their talks again.